All right, so naming parts on this. I mean, there's lots of things you could have done. Uh, concrete shield, lead shield, or you could have said that this whole thing was the containment. The something we didn't talk about is this piece right here is the most notable portion of a nuclear power plant because it's huge, and nobody realizes that that's where the nuclear power plant is. They just assume that it's inside this thing. But again, this thing is just a giant water slide for water. You can put, pressurizer is here, the steam generator is here, the control rods are here, condenser, pump, fuel assembly. Could have said this is the primary loop and the secondary loop, condensing loop, cooling loop, cooling tower, water vapor. Yeah, lots of things you could have written down for this.
Is the what is the thing called that turns? I don't know why I'm not
The
remembering it.
turbine?
But yeah, does the turbine actually move? Is it the thing that actually moves the
Generator?
yeah.
Yes. The turbine is coupled to the generator by an axle. So when the turbine turns, the generator turns.
So how big is the turbine?
It's huge. I mean, you saw that generator that the guy was standing on in that photograph. And so the turbine is different shapes depending on if water or steam is going through it. But I mean, think about how big the blades are for wind turbines.
Yeah.
So huge.
Huge.
All radioactive atoms eventually become stable. How does an atom that is radioactive become stable? So what has to happen?
The nucleus decays.
So the radioactive isotope decays, and what happens?
Alpha and beta particles are released or added.
That's it. So I've got a radioactive isotope. It decays. The product that's created is a new isotope, and it either is or is not radioactive. And if it's not radioactive, then the process repeats itself until it becomes stable. So all radioactive substances eventually become not radioactive substances. Probably should have swapped these question positions, but why or why is it difficult for radiation to leach into the river?
Because each of the loops is not, they're not connected, they're separate.
There's just so many loops as well.
There's four different loops. None.
If one loop breaks,
Touch.
the whole system is shut.
One breaks. Whole thing. So people who don't know anything about nuclear power would talk about the fact that these nuclear power plants would, as they're running, they're leaking radiation into the river here. That's utterly ridiculous, right?
Mm-hmm.
Because this is where all the radiation is. And those are sealed. So if they broke, we'd turn it off. Alrighty. What's coming out of the top of the cooling tower? Just water. And then, did you guys find this?
Oh, yeah. Safety control rod accident.
Did anybody find out what that meant? Nothing?
Didn't it have to do with the difficulty situation? Control rod.
Yeah. At the University of Chicago, there was a basement building that was a gymnasium that they turned into their nuclear testing facility. And in it, they built this. So in the middle of this is the first nuclear power core. And there's a bunch of lead and a bunch of concrete bricks here. So the concrete's there to block the neutrons, the lead's there to block the gamma radiation, and the alpha and beta can't get through any of that stuff. So there is a not too visible. You see this? There's like a line right here. You know what? I'm gonna grab this whole image. Cut. Copy. Go back over here. There's a line right here, and there's a pulley. There's a control rod that you can't see that's right here, and there's going to be a guy standing right here on this rail, and this guy's got an axe. He's going to cut the line, and when he cuts the line, then the control rod will fall into the reactor and turn it off. Okay, so he's standing there just in case some bad stuff happens.
That's his whole job.
That's his job.
Stands there
just stand there.
and waits.
Unless something bad happens. So the funny part about it is, or interesting part about it, is this is what somebody says when they need to turn the reactor off today. So we ran thousands of drills in the 4 years I was on the aircraft carrier, and a third of the drills forced the reactor to be scrammed. So you scram the reactor, and that's shoving those control rods in and turning it off. But it still stems from this safety control rod X-Man thing. That's the guy's job, and they just thought it was funny, so they just kept it. So if you want to turn the reactor off right now, you scram the reactor, even though there really isn't no longer a human standing there with an axe to cut a rope. If you watch,
I was like, has that been outsourced?
Yeah, it's been outsourced by a spring and a solenoid and some electricity. So if you watch movies, though, that they have nuclear power plants, they say this. So now when you see that, you know what's going on. Alrighty, so why did this graphic irritate the hell out of me?
Because they got it wrong. Nuclear fission produces, I think, is it nuclear fission that produces more energy? Yeah, nuclear fusion is so hot that no container on Earth could actually move it.
Yeah, so the fact that they say a smaller release of energy is just stupid, right? This is
incorrect, yeah.
This is utterly wrong.
And then nuclear fission only releases enough to just about boil water.
No, that's not true.
Well, you said it.
The way we have it set up, no. Remember what the temperature of the primary coolant was? Do you remember the primary coolant was pressurized to 2,000 pounds? Why was it pressurized to 2,000 pounds? Because the water temp was 525 degrees.
So it didn't boil?
It didn't boil. So it's way hotter than boiling water. We're just using it to turn steam, water into high pressure steam. But regardless, the water temp is 500 degrees, and there's a tiny bit of uranium compared to the amount of water. And we all know water is difficult to heat because of its specific heat. Some other stuff with this is not the end product.
Yeah, that's definitely not an alpha particle.
This right here is hydrogen and deuterium. That's great. This right here is hydrogen and that's deuterium. What's this thing right here? Hydrogen. This is tritium and a proton. Well, oh wait, sorry, they're calling it a free neutron. Regardless, this is hydrogen or helium-3. No, it's helium-4. That is wrong. What about this picture right here? If this was the case, that would be amazing. Because what happened is the nucleus was separated into protons and neutrons. And so what would your waste be? Hydrogen gas and neutrons? There would be nothing radioactive. This doesn't happen. We get two big chunks, and both of these have half-lives of somewhere around 100,000 years, which make it terrible. So, being irritated with this, I looked up the phone number for the University of California, Los Angeles Physics Department. So, what's the abbreviation for University California, Los Angeles?
UCL? Berkeley?
UCLA.
UCLA?
This is UCLA. So I looked up UCLA's physics department and I couldn't find a phone number. I thought that was a little strange. So I found the science department's phone number and I called and I told this this woman who answered the phone about this article, and she said that was strange, and she passed me on to the science department chair, and I told this person about it, and he said, we don't have a physics department. This is citing UCLA's physics department. They have a science department in which physics and chemistry and biology and a bunch of other stuff is inside, but there is no such thing as a physics department at UCLA. So the author lied right off the bat, right there. So the author or the science department chair was irritated, and he's like, can you send me the article? So yeah, I took pictures of it and emailed it to him, and I waited until he got it, and he opened it up, and he's like, well, that's wrong. This whole thing is wrong. I'm like, yeah, that's why I'm irritated. And then he's like, wait, it says physics department. We don't even have a physics department. So we go through the whole process independently and realize this person was an idiot, and they completely lied about it. And so then both of us tried to track down the author, and the Associated Press wouldn't give us information to get access to the author. So that's just sitting out there, floating around in the June 29th edition of 2005 Oregonian. But more importantly, do you all know what the Associated Press is?
No, I've heard it a lot though.
What is Peter Parker? Does Peter Parker have a job?
Yes.
No, he does not have a job.
What?
No, Peter Parker doesn't have a job.
So you're saying
I
it's
thought he was a
freelance?
It's freelance. Peter Parker is a freelance photographer, of which the Daily Bugle occasionally purchases pictures of Spider-Man, but he doesn't have a job. That was like a big sticking point in both the comics and the movie. I want a job. Nah, freelance. Freelance is the best thing for a young kid like you. So no, not getting a job. So what the Associated Press is, most of the reporters are freelance. So they write a story about something that happened. They submit it to the Associated Press. The Associated Press puts it on a wire service, and then newspapers will grab articles that they want to include in their newspapers. So usually this kind of thing happens when they need space to fill, or there's something important, like the Oregonian probably didn't have a journalist that spent much time in Afghanistan. So if they wanted to put an article about Afghanistan, they'd go to the Associated Press, take one of their articles, pay them some money, then the Associated Press would pay the person who wrote the article. So it's all freelance work. So this is a freelance person, and the reason this is a bigger problem is because it came off the Associated Press. So who knows how many newspapers ran this? It's still on there though. Like if somebody who has access to the Associated Press wanted to like if something happened with nuclear fission or nuclear fusion, they could still put this article up there. So it irritates me that we found out at that point in 2005 that the Associated Press doesn't fact check the articles that come in.
I could make stuff up.
No, because you'd have to be on the Associated Press.
Oh, I was gonna
So
say,
you have to
usually they
submit a
know
resume,
to
and
make stuff up.
they'd accept you. You'd probably need a degree in journalism. Maybe not anymore, but certainly in 05. But just frustrating that I thought it was a good source, and it turns out to be a terrible source.
The more you know, I guess.
Well, yeah, I mean, I knew enough to know that this was BS, but I don't know enough to know if other things are BS because I don't know about those topics like, you know, I don't know, welding. Okay, so let's go on to the notes. Sorry, it just got warm in here.
Tis the summer.
Okay, so this next topic, hybridization, this is going to be easy for us because we already talked about this, right? So Pauling said, hey, the reason that the carbon atom can make 4 bonds is because the 2s and the 2p are so close in their energies that we hybridize the orbitals and we say that there's an sp3, and so that means one of the orbitals was an s and 3 of the orbitals were a p, and I mathematically add those things together to get a tetrahedral shape. If I'm an sp2, then I take one of the p's and remove it, and it's just a regular double teardrop orbital, and then I take an s and 2 p's and add those together, and I get a trigonal planar. And then if I just make it sp, then it basically just looks like 3 separate teardrop-shaped orbitals. Okay, so hybridization is why the carbon atom can make 4 bonds. So let's talk about some general properties for organic molecules. Honestly, they're mostly boring. The molecules that we're going to talk about are basically all alkanes, and they're super boring molecules. They don't really do anything. They're flammable. But until I put a double bond on them or start adding what we call functional groups, they're super not super useful. But it's easy to change that. So flammable, they have almost invariably they have a high vapor pressure. Even the very, very long chain stuff, you can smell that. They're covalent bonded, they're nonpolar. So their solubility in water is low or 0, depending on what how big the molecule is. They're usually gases or liquids at room temp. We talked about the fact that carbon, hydrogen molecules with 1 carbon, 2 carbons, and 3 carbons, those are natural gas, and those things are gases. And then that butane was the 4th one. And that is the stuff that's in a lighter, and it looks like a liquid until you push the button, and when it comes out, it's a gas. So 4 carbons is the break point between being a gas or a liquid. And then we knew the octane molecule is gasoline, and so that we know that that one's a liquid. And we know that gasoline has a high vapor pressure because if you're pumping your gas, or somebody's pumping your gas for you, you usually can smell the gasoline almost immediately when they start pumping. Or you just smell it when you pull into the gas station. Yeah. And it's not conductive. So it's a non-electrolyte. If you put bare wires that were hot into gasoline, you might think it'd explode, but it wouldn't do anything because there's no way for the electricity to jump from one side to the other. Okay, so we're going to talk about some formula types, and we've definitely seen chemical formula, and I've put structural formula up, and we've actually seen condensed structural formula when we talked about acetate, but we haven't seen line structure before. So this is the butane molecule. It's C4H10, and this is kind of useless. Not useless, it's just not super helpful. All I know is I got 4 carbons and I got 10 hydrogens. So if I want to tell you or show you exactly what it looks like, then this is it. I've got 4 carbons, they're all connected to each other, and then I've got hydrogens around the outside, and each one of those carbons is showing 4 bonds. The condensed structural formula just makes it so I can type it into like a Word document or even on a typewriter. Nobody wants to do the structural formula on a typewriter. And then the line structure is how most chemists draw organic molecules. So what are we looking at with the line structure?
Isn't each point representative of the carbon or 2 carbons?
Each point is 1 carbon, and each one of these lines is a bond between carbons. So what are you not seeing?
We're not seeing the H's.
We're not seeing any hydrogens, but you're supposed to know, since you're studying organic chemistry, that carbons need 4 bonds. And so if the hydrogen is not drawn, then assume it's there if the carbon doesn't have 4 bonds on it. So This this one right here on the far left hand side is all of this.
So in
And
organic
this right
chemistry,
here, this corner right here, is all of this.
is this only used with carbon and hydrogen formulas?
It's only used with organic, a little bit of biochemistry, but mostly just organic. And then,
And organic always has carbon, right?
yeah. So if I draw something like, we all seeing that line structure there? How many carbons does this thing have?
4.
1, 2, 3, 4, 5. All of the ends are carbon and all of the turns are carbons.
You're frozen. I'm not getting
Can you guys see me, the 1, 2, 3, 4, 5 I've drawn?
Okay, yeah, there it is.
It's on the right hand side. It's brown with red
Yeah,
letters.
It was probably covered. It was probably covered by all the. I went into full screen.
You guys good now? Everybody else? Okay, so tell me about carbon number 1. What is carbon number 1 connected to?
3 H's.
And carbon number 2. What's carbon number 2 connected to?
2 H's and 2 carbons.
Yeah, 2 H's that aren't shown, and carbon number 1 and carbon 3. Tell me about carbon number 3.
Is carbon number 3 just connected to the other carbons?
Well, how many connections to other carbons is it making?
3, it looks like.
So it's connected to carbon 2, 4, and 5. So that's only 3 connections. So what's not being shown?
1 hydrogen.
So there's 1 hydrogen there. And that's how you do it. And this is what scares people about organic chemistry. That's all I can say. Let's talk about sources for organic molecules. So
Wait, what would that structure be called?
we'll get to it, but it's 2-methyl-butane is its name. Where do we get these organic molecules from?
Nature?
Okay.
Things.
Specifically, we're going to get almost all of this from crude oil. So carbon chains from 1, 2, 3, 4, all the way up to 50. They're all coming out of a barrel of crude oil. We can take those molecules and do something called cracking, and that cracking allows the molecule to change its structure. So maybe if I'm looking at gasoline, let me come up with a new. So we okay with that? Why is the formula for gasoline C8H18? Why 18?
There are 18 hydrogens connected to the carbons.
Sure, but why?
They aren't in a straight line structure.
No, it is in a straight line structure. Well,
Each carbon,
sort of.
each carbon needs 4 connections.
Okay.
And you have 8 carbons, so that already makes 16 connections, and then you need 2 on each side. Maybe.
Okay, so every single carbon in the chain is connected to 2 carbons, right? So the carbon in the middle of a chain is connected to the carbon in front of it and the carbon behind it. So 2 of its bonds are carbons. And then the other 2 bonds are hydrogen. So for every single carbon, I need 2 hydrogens, right? And then what Annika said, then the ones on the end need to be basically capped with a 3rd hydrogen. So whatever your alkane value is, so if I've got 10 carbons in my chain, so double it and add 2. So if it's a decane molecule, it's C10H what?
20?
2. 22.
See, 22. I thought you said H2. I was like, ah!
So double that number and then add 2, and that's how I get my 22. Okay, so this molecule, so when I go to draw the line structure, I put my writing utensil on the board and say 1, 2, 3, 4, 5, 6, 7, 8. Because what people do when they first start doing this is go 1, 2, 3, 4, 5, 6, 7, 8. What's wrong with that?
That's 9.
That's 9. So you put it on, there's 1, but if you say 1 when you go to the first connection, I've already got 2 molecules there. Okay, so this is 1, 2, 3, 4, 5, 6. This is octane. Poorly drawn, but regardless. This is a bad molecule. It's a bad molecule because it will ignite at a low temperature. So do we know how an internal combustion motor works?
You add gasoline.
You add a hydrocarbon, sure.
Hydrocarbon. And then
Here it is. So this is your typical 4-cylinder motor. So what do you notice immediately?
different colors.
Okay. So what color do you think is the color of the explosion?
Red.
The orange-red, right? What do you notice about orange-red?
It's moving from right to left or left to right.
It's actually jumping from spot to spot. It's not moving from right to left. It's more random than that. Well, it's not random at all. It's number 1, number 4, number 2, number 3, number 1, bouncing around like that. But what you should notice is how many cylinders are exploding at a time?
Only one at a time.
Only one at a time. That's it. So in your 4-cylinder vehicle, you've got 1 cylinder exploding at a time. What are the other cylinders doing?
Are they cooling it?
No.
They're creating.
If I want to explode something, what do I have to have in the chamber?
Taking air, exhausting.
I've got to have oxygen and fuel, right? So somehow during the process, I have to add oxygen and fuel. And then after it's exploded, what's inside the chamber?
Water.
And
Water and hydrogen.
carbon dioxide,
Carbon dioxide.
right? It's burning a hydrocarbon. So water and carbon dioxide. So that's exhaust, and I need to get rid of that. So there are 4 steps. So there's an intake step where the fuel and gasoline come in. So let me let's look at this one because it keeps moving, and we'll go back to that in a sec. So this is my intake valve. So this valve opens up, and this valve opens up when the piston is going down. And what comes in here is what's coming from your carburetor or from your electronic fuel injection, which is air and fuel in the correct ratio, okay? When this guy gets to the bottom, this valve right here closes. And now I'm here. So this is coming up, and this is called the compression stroke. So all of these gases are being compressed. When it gets up to the very top of the rotation for the piston, then the spark plug sparks. When the spark plug sparks, it shoots the piston down, and this is where your vehicle gets power from. This piston's up and down motion is turned into a rotation, which is pretty cool. Everybody okay with that? All that's happening is a piston is going up and down, and the way that the camshaft and the rods work is it turns that up and down motion into a rotational motion. So while this is happening, the piston goes down. Again, the valves are still closed, but when that piston comes back up, the exhaust valve opens and it pushes all of the carbon dioxide and water vapor out the exhaust valve. And then I go back to the intake step where it starts to go down, the intake valve opens up, and then the air comes in. So if we flop back over to the other example, you can just pick 1 cylinder to look at and watch what happens. So can you see from this diagram why it would be really important that all of the things that are happening happen at the right time?
Yeah, because if there's two explosions at once, or if there's no explosions, then
Or if it's exploding when it's not to explode. So if your car is incorrectly timed, the timing is off, bad things can happen. Okay? Imagine if during the upstroke, after the fuel and exhaust have already been intaked, it just ignites. So right here, look at this compression stroke, both the valves are closed, and this thing right here has fuel and air in it. What if while this is trying to make its way up, this explodes early? Why is that horrible?
Because it'll push it back the wrong way.
Right. This thing hasn't gone over the rod isn't over the hump on the cam. So it'll actually try to slow your car down. Obviously not what you want to do. So what you want to make sure is this fuel and air in here don't explode until the spark plug sparks. But if I put octane, straight octane in there, it will explode because the temperature at which the octane will burn is pretty close to the temperature at which your motor runs at. So bad. So what we do instead is we do a little chemistry on it with some with some catalyl, and we end up with this molecule. So what's the same about these two molecules?
carbons.
Same amount of carbons and?
Same amount of hydrogens then.
Yeah, these are structural isomers of each other. They are the same chemical formula, but different structures. Can you see why the chemical formula is not super helpful?
Oh, yeah, because it doesn't really show you what structure it could be.
In organic chemistry, this molecule is highly sought after as a fuel. This molecule is, you do not want that in your gas tank. But they have the same chemical formula. The difference is when I have a shorter molecule with lots of branched chains on it, the temperature at which it ignites is a lot higher than what you would expect if it was, than what it would be if it was a straight chain.
So what do you call that one then?
This one right here, how many carbons is it long?
Long?
It's 5 carbons long. We okay with that? 1, 2, 3, 4, 5. I have these other carbons hanging off of it, but it's only 5 carbons long. So this is a pentane, because pent means 5. And then we would discuss these side chains that are on it, which are all methyl groups, meaning they're all 1 carbon. So this would be 2,2,3 trimethyl pentane, which might sound like a mouthful, but after today, you won't even think it's a big deal. So
what about like if we have another formula that actually only has 5 carbons? What would we call that one?
I'm sorry, say that again.
What if we had a formula that actually only had 5 carbons in it, so it was C5H
12. Then it's just pentane.
Oh, okay.
Okay, so do you guys know what this is? Have you seen something like this? I mean, you must have, but do you understand what it is that you're looking at?
No.
Let me, hey, what happened to my, that's irritating. No. 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 Oh yeah, there it is. What am I looking for? What are we doing? Oh yeah. Everybody okay with this image being an oil refinery? I know we don't have any in the Pacific Northwest. They exist in California, but mostly Texas and the East Coast. So when oil comes in, it's a homogeneous mixture. but all of those things don't do the same thing. So I need to separate the homogeneous mixture out. So you guys had a homogeneous mixture of ethanol and water, and what did you do? You separated it out based off of its boiling points, right? So this large tower thing is this thing right here. So what we have here is I dump crude oil in here and I heat this up. It's incredibly important to understand that this pipe is closed, okay? Meaning it has zero access to air. And that has to be the case because this is 370 degrees Celsius, which is considerably higher than the flash temperatures, the ignition temperatures for these different hydrocarbons, all right? So I heat it up to a very high temperature, 370 degrees Celsius, and most of these substances turn into a vapor. And so when they come out of this tube right here, most of the substances travel up. Not everything. Some of it comes out as like a, I don't know, like a molassesy kind of substance. And they go down to the bottom of the container where they never got turned into a gas. And do you recognize some of the names here?
Heresy.
No, down here.
Isn't that for like light?
Right here.
airlines?
The stuff at the bottom, that's at the bottom. You seen any of those words before?
Wax is for-
Obviously, you know asphalt. Were you aware that asphalt is basically the dregs of a barrel of crude oil?
So is it cheap?
It's not that it's cheap. It's just that the roads that you're driving on literally are, dead plants that have decayed. They're fossil fuels. So what's going to happen to the fossil fuels?
They'll run out.
So what are we going to do for roads?
Haven't we been having like I know in Los Angeles they've been starting to they're just panning the roads right. It's not like
Dirt road.
concrete.
That's not going to be very easy, a dirt road, when it rains in Oregon.
I mean, everyone fend for themselves, right?
So we can't do this forever, is really what I'm saying. The roads could be made out of concrete, but the concrete road is phenomenally more expensive than an asphalt road. And you probably have noticed that on super hot days, the asphalt road smells a little bit like bad oil or something because it's oil. That's what you're smelling. Coke is just basically looks like coal. And paraffin wax, we have that in lab. That's that parafilm stuff that you stretched over the beaker to make a vapor seal. Do you guys know when we got the interstate system in the United States?
Like the 19 World War I.
No.
Because
No.
not World War. I know they.
No world wars.
It was the Great Depression.
No. 60s. Early 1960s. Harry Truman and Dwight Eisenhower. The two of them, one right after the other, they were talking about this is what we want to do, and we want the. So, what was the reasoning behind building interstates?
So you could
I don't
plan
know.
travel.
Easier.
Commerce. If you go to the store and you buy something, how did it get there? A truck brought it there. Could you imagine the Fred Meyers in the Dalles being stalked by the scenic highway? Think about Rowena Crown and how narrow and windy the Rowena Crown is. Or the twin tunnels between Hood River and Mosier. That was open to trucks and cars. Think about how long it would take to get food from Portland to the Dalles. Forever. Or how long it took cherries to get from the Dalles to Portland. They had to take the river, right? There wasn't a good way to do it on road. So they wanted to increase the economic power of the United States, so they built interstates. So roads like SR 14 were important roads, and then I-84 came in, and everybody drives I-84 because it's, you know, wider and faster and more safe. When this happened, they talked to everybody in the government, and one of the entities of the government, the Department of Defense, made a request. And the request that they made is portions of the road, this interstate that they're building, were made out of concrete. Does anybody have any idea why the Department of Defense would request certain portions of the road to be made out of concrete when concrete's like 100 times more expensive?
Didn't you
So
say it
that
was
it
for
wouldn't-
Did we talk about this
fighter
already?
jets so that- We did. They landed the fighter jets on it, and so the concrete wouldn't melt. Because the
Not
fighter
melt.
jets wasn't-
Not melt. I'm not worried about melting. I'm worried about what? Technically, what is asphalt?
Oil.
So
You
if
don't want it to burn.
I don't want it to catch on fire.
asphalt was-
Oh.
So if I land a fighter jet on an asphalt runway, it will catch on fire. The asphalt will. How do you put out an asphalt fire? You don't.
It's an oil fire, so you don't. Yeah,
You
just let it burn.
you bring an excavator in and you just cut the road and it burns itself out. There is no way to stop it from burning. This happened in Philadelphia. Did we talk about that? The tire factory that caught on fire? They just had to cut the
Yeah,
road.
It's still burning today.
No, that would be horrible.
I know there's a town that's still burning underground today.
Oh yeah, that is in Pennsylvania.
So there's
There's
like a pit to hell where it's just a bunch of methane burning.
no, it's not. It's coal.
Well, I mean, there's a place like in Europe, I think that's like that.
Gotcha. Okay, so the other substances inside this barrel of crude oil go up, and this is all baffled, meaning the gases have to go through sort of like a maze. So they go up, and then they're forced to turn, and they're forced to turn, and they're forced to go all these different directions. And that's designed to cool it as it travels away from the heat source. So when these liquids get to here, they'll turn in, or these gases will turn into a liquid, and they'll come off here. And this is like lubrication kind of thing, like the stuff you'd put in a wheel bearing. So a wheel bearing is supposed to keep friction down inside of like the wheel on your car, which is driving, I don't know, 70 miles an hour. And if the friction is too high, then that thing will heat up, expand, and seize, and then your tire won't turn. So you need to make sure that this oil, even at high temperatures, stays slick and stays as sort of like a gel instead of turning into a liquid. Because if it turns into a liquid, it'll just run off, and then you'll have no lubricant there. So a little bit, and these guys are carbons between 16 and 20 long. A little bit farther away, we get carbons that are 15 to 18, and these are things for like diesel fuel for like trains. So longer carbon things, it takes more energy to get it going, but it's sort of like more bang for your buck once you get it going. And then further away, higher up, I get smaller carbon chains. These are 16 or 12 to 16, and this is like regular diesel for your car, stuff I can use for cracking, kerosene and whatnot for lamps. I get further away, and I can get to the important number, which is 8. Why is 8 the important number?
For fuel?
For octane. So when the nation realized that automobiles were going to be important to its economic development, they looked at hydrocarbons and said, okay, well, I got this barrel of crude oil. We got this thing out of Pennsylvania. Which one of these can we burn in a car? And they're like, well, anything from basically like 12 carbons down to 1 carbon. Well, which one of those is the most? Turns out 8. 8 carbons is the thing that comes out of crude oil the most. So they decided to build motors that ran off of 8 carbon gasoline. So that's why we run off of octane. And then you can see that carbons 1 through 4 are up top because they're gases at these temperatures. And 1 through 3 are natural gas, and 4 is that butane molecule. So all this stuff, our whole economy is built off the fact that we could steal this stored energy out of the ground. And at some point, we're going to run out of that, and our economy had better be shifted or we're hosed. So remember that Wohler disproved that vital force theory, saying you can make organic molecules? So have you purchased synthetic motor oil before? It's significantly more expensive, right? but it also lasts a lot longer. If you buy synthetic motor oil, you literally can just change the oil filter out. You don't have to change the motor oil. It's good for like 4 oil changes, 4 filter changes before you need to change the oil out. And the reason is that's made in a lab, starting with natural gas. So what is not in natural gas? That's in crude oil, dirt. So the reason that the synthetic motor oil is better for your vehicle is because it doesn't come with impurities. They made it out of a gas that they made themselves in a lab, and again, they didn't throw any dirt in there, so it's just simply better. So there isn't stuff to turn into tar. Okay, so let's talk about
What is carbon?
long chain carbons. Let's talk about functional groups. You're going to need to recognize these things.
So are they all just like things that you could attach to a carbon chain?
Why can I not get this exactly where I want it? That's really frustrating. There we go. Can you guys see all of that? Okay, so what we're looking at are the non-boring portions of organic molecules. So in an organic molecule, if I attach these different functional groups to it, then the molecule itself will have some functionality. So this is a super boring molecule. This is ethane. So this is one of the 3 natural gases. But what happens if I put an oxygen in between that hydrogen and that carbon?
It changes to a less boring molecule. Amazing.
Is this molecule different than the other molecule?
Yeah.
Obviously.
Now you can drink it.
It's fundamentally different. 1, it's a liquid at room temperature instead of a gas. 2, it can inebriate you instead of just catching you on fire. Not that it can't catch you on fire, because it can. I found this lab after we started like a month ago that I wish I would have known about before we started this class. It was about to find out how much ethanol or isopropyl alcohol was in hand sanitizer that you purchase. And you figured it out based off of burning hand sanitizer. So
Oh, wow.
next time, fall term, there are going to be people in their kitchens catching hand sanitizer on fire in like fry pans.
Does this mean that alcohol is acidic, or is that just...
Nope, not acidic in any way, shape, or form. Alcohols are not. But we're going to talk about what makes something acidic in an organic molecule here in just a sec.
sick?
So, if I have a carbon, and that carbon is attached to another carbon, and that carbon has 2 bonds to an oxygen, and then on the other side of the carbon it's an H, that's an aldehyde. Where have you heard aldehyde before?
Formaldehyde.
Formaldehyde.
Put in-
Okay, so you want to preserve things to keep dead things dead and not decayed. So what do you think formaldehyde does to things?
Does it coat them?
Does it what?
Coat them.
No? Why do you put like a pig heart in formaldehyde?
So you can dissect it later.
But that's not helpful. What else we got? Anybody else?
I mean, it would prevent oxygen from getting to it, but what other things to prevent it from spoiling?
Okay, well, the answer is we put formaldehyde on the pig heart to keep it from spoiling. Well, what causes something to spoil?
It is exposed to oxygen.
And
bacteria and
Bacteria.
bugs and
So
life.
formaldehyde kills stuff. So if I put something dead in it, no big deal. It's already dead. But what's not going to happen is live stuff like microbes are not going to go into a pig heart that's soaking in formaldehyde and make it decay because it can't live in formaldehyde, which is why you use formaldehyde to preserve things. So this preservative is there to make sure stuff is dead. So what other preservatives do you know about? What?
Vinegar.
Vinegar. Why is vinegar used on pickles and meat?
It's delicious.
There's a theme
To kill the microbes.
to kill
Everything.
microbes. So vinegar kills microbes. Well, what else do people use to preserve stuff?
Mm,
Salt.
Salt. Salt kills microbes. What else do we use to kill stuff? Sugar.
Hmm.
Think about the sugar that's in your kitchen right now. Is it in the refrigerator?
no.
Yeah.
Is it in a sealed container?
Yes,
Yeah.
because ants.
No.
You don't have to, but mine's sealed because sugar ants.
Because of what?
Sugar ants. We have
Ants, they like to get into it.
There's one type of ant that will do that, and that's it. Because there's no moisture there, so all the other bugs literally die in it because there's no water
Yeah.
around.
Yeah, but
I mean,
without
think about
sugar,
the
you
sugar
just
at the
put it
grocery
in a
store.
paper bag.
It's just sitting in a paper container, right? Because you don't
Yeah.
have to worry about bugs because almost no bugs can handle the fact that it's that dehydrated. Okay, so what do you need for an aldehyde? I need a carbon doubly bonded to an oxygen, and on one side of the carbon there has to be a hydrogen. What about an ether? An ether happens when I've got an oxygen, and it's singly bonded to carbons on both sides of it. Where have you heard ether before?
Like fantasy
Party
stuff.
fluid.
Fantasy. Oh yeah, sure. Like the ether.
Like
What'd
the
you,
ether.
what'd you
yeah.
say, Sheen?
I don't think he heard you.
Starting fluid like is it di
Oh,
ether?
diethyl ether is good to get a motor that's having trouble started. It's also what physicians would use, say, during the Civil War to knock a person out right before they sawed their leg off. That's what the beginning of Dances with Wolves is about. A guy not wanting his leg sawed off. So they don't use ether anymore because, one, it's a respiratory irritant, so it could cause a lot of respiratory problems. And two, people would wake up during surgery. I don't want to have to wait. I don't want to wake up in the middle of somebody cutting through my leg with a bone saw.
Sorry, Scooby.
Okay, so the next one over is called an ester. So the ester is kind of like an ether, except instead of it just being two regular carbons on each side, one of the carbons is doubly bonded to an oxygen. So the difference between the ether and the ester is one of the two carbons has to have this on it. The other, on the ether, these are just regular old carbons not doubly bonded to an oxygen. An alkyne is anytime I've got a triple bond.
Anytime can it be with
Anytime.
like
two-
oxygens?
No, you can't make a triple bond. So anytime I've got three bonds between two carbons, it's an alkyne. And it's spelled with a Y-N-E. And an alkene, which is E-N-E, is a double bond. And all of these carbon-carbon single bonds, these are all alkanes. So the base molecule is an alkane, and then I add these functional groups to it. This is a carboxylic acid, and we've seen this before. So this kind of looks like the ethanol over here. I've got a hydrogen and an oxygen, but the difference is the carbon that the OH is attached to is doubly bonded to an oxygen, and that makes all the difference in the world. This hydrogen right here is an acid. This hydrogen here is not an acid because this carbon here is just bonded to carbons and hydrogens. So here's an alcohol. Anytime an OH group is attached to a carbon that is just a regular old carbon, this is an amine, meaning a nitrogen attached to carbons. It could be attached to one carbon, two carbons, or three carbons. If a nitrogen is attached to carbons and they're just regular carbons, meaning no C double bond O, then it's an amine. This is different though. This is a nitrogen attached to this carbon, but because this carbon has a double bond O, this is an amide. They're fundamentally different from each other. One of these things will cause your heart to race, and one of these things will cause your respiratory system to be depressed. And it's just because I've got a double bond O or I don't have a double bond O. If I see this benzene ring in a molecule, I'll call it phenyl or I'll call it benzyl. One of those, either of those is fine. If I've got something from the halides attached to a carbon, I'm going to call that an alkyl halide. If I've got a carbon doubly bonded to an oxygen and on both sides I have a carbon, then this thing is called a ketone. And
ketones are what makes us fat. I think.
fructose is a ketone. And fructose is immediately turned into fat if it's not utilized by blood sugar. And what's the prefix hetero mean?
Hetero means
Different.
opposite.
Different.
Opposite.
And so this is a ring, a cyclic ring. And in this ring structure, I've got 2 nitrogens and 3 carbons. So that makes this a heterocyclic ring structure. And these are important because this is what your DNA's bases are. Carbon rings with nitrogens spiced in there. So every single molecule that has one of these functional groups has a dramatic name change. We're not going to learn that. We're not going to learn how the name of a molecule changes when an amide is added. I am going to require you to be able to recognize that a molecule has an amide on it, though. Okay, so let's talk about the base molecule, the alkane. So this is the first of the organic molecules. It's the simplest of the organic molecules. We've already talked about its base formula, which is carbons and hydrogens, and the hydrogens are double the carbon number plus 2. The nomenclature comes from this IUPAC, International Union of Pure and Applied Chemistry. And so if you look at something as simple as like aspirin or testosterone, those just have simple names, but they actually have a super complicated name as well. Depending on what molecule it is, it might have a really, really long name, like let's go Q, homework. I gave this homework to the 121 students today, and I gave this question to you before. You guys have already seen this question. Cinnamon is called cinnamon, but this is its actual IUPAC name. There's vanilla, and that's its IUPAC name, meaning that's the actual chemical name for the substance. So why do we call it cinnamon instead of calling it 2-E3-phenylprop-2-enol?
Because it'd be awful to try and say all the time when you want to go to the store.
Right. Do you want some 2-E3-phenylpropyl-2-enol bun?
And they'll probably also scare people because they don't know what that is.
Do you want to go to that place in the mall, the 2-E3-prop-2-enol bun? Cinnabun, right? Yeah. Do you want some 4-hydroxy-3-methyl-ox-benzyl-aldehyde in your latte?
That's delicious.
So it always drives me crazy when people put up like chemical names for things and say, do you really want to eat this? This is in your coffee. This is in your, I don't know, granola bar that you eat. Like, yes, cinnamon is yummy. Vanilla is yummy. Your ignorance irritates me. This is right along the lines of dihydrogen monoxide, right?
That was hilarious.
When I see you in like 8 years on the streets in Hood River, you're going to say, remember that dihydrogen monoxide thing you got me on? Or you're going to say, the railroad track, I still use it. Those are the only 2 things anybody ever says, besides hi.
That'd be fun.
Okay, so let's talk about nomenclature. So we need to be able to name some of the simple molecules. To name a simple molecule, all of them have a root, and all of them have a suffix, and some of them, well, most of them have a prefix. So the prefix is going to talk about side chains and substitutions. The root is going to talk about the longest continuous carbon chain, and the suffix is going to tell me what kind of molecule is it. So if somebody says ethanol, I know that this is a 2-carbon chain with only single bonds that has an OH group on it. So it could be a really long name like, oh, I don't know, this name here. So this tells me that this is an aldehyde because aldehydes always end in AL. So the suffix for this thing is an aldehyde. It's also telling me, since we see this phenyl thing in there, that somewhere in the cinnamon molecule there's a benzene ring. All right, so let's we didn't actually go over this. We talked about it a little bit, but we didn't go into great detail on this. But the prefixes that you're going to need to know to name these molecules are, most of them you already know. So you should already know 10, 9, 8, 7, 6, 5, and that's it. You should know pent, hex, hep, oct, non, and dec. The ones you probably don't know are meth, eth, prop, and bute. Sorry, I wasn't there when they made these rules, but meth means 1, eth means 2, prop means 3, and bute means 4. And then the rest of them are the ones that you already know, like obviously pent is 5, and hex is 6, and dec is 10. So we're going to use these as roots. And then depending on if there's functional groups or if they're double or single bonds, then I'm going to give it a root name. Okay, so
somewhere.
these are 2 ways to name, well, let me run through this real quick. These are the rules. I find the longest continuous carbon chain, and I give it a root. The chain, whichever end of the chain is closest to a substitution on the chain, and a substitution means a hydrogen has been removed and something else has been added. It could be a carbon, hydrogen, could be a butane, could be a fluorine, doesn't matter. If something else has been added, that's a substitution. I give the location of the substitution based off of its position from carbon number 1, and then I use some syntax, meaning I put dashes between numbers and letters and commas between numbers and numbers. So that sounds like gibberish, but let's do an example. So this molecule is called 4-ethyl octane. Why 4-ethyl octane? Because if I start at any of the ends, if I start here or here or here and count to another end, the longest continuous chain that I'm going to get is an 8. So if I start here and go there, or start here and go there, I get 8. So why am I calling this guy here number 1? Because
closest to the first substitution.
Yeah, so this is a substitution. This is a 2-carbon chain where there should be a hydrogen. And what end is this thing closer to? This end here. So this guy immediately, after I've determined that it's 8 carbons long, this guy gets to be number 1. And my substitution is coming off of carbon number 4. So I write down, when I first started doing this, I just wrote down the root. So I know it's an octane. Okay, what's on my octane? Well, I know the thing that's on my octane is 2 carbons long. Are we okay seeing that that's 2 carbons?
Yeah.
I don't like that there's a third one.
There isn't a third one.
2, 3.
This is,
3 isn't.
that's 1 carbon, and that's 1 carbon on the side. The third carbon, why is this not part of the side chain?
Because it's 4.
It's carbon number 4 in my 8 carbon chain. Okay? So that's why it's not included. I see that there's 3 carbons in a row here, but this carbon right here is part of the main chain, so I don't count it. Okay, so I've got 2 carbons here. So then I write F, and then YL means side chain. And then you have to tell me where this 2-carbon side chain is, And the answer to that is coming off of carbon number 4. So this is the actual correct IUPAC name. What about this one? Why am I calling this one incorrect?
Why?
Started nothing from the wrong end.
I started counting from the wrong end. Okay, so somebody tell me what the purpose of a name for a molecule is.
Make it easier to identify, isn't it?
Anything else? Something more germane to the issue?
Oh, it would differentiate it from other molecules that are at least similar.
Anything else? What should you be able to do? What should you be able to do with the name?
Build it.
Yeah, you need to be able to actually draw the structure. Okay, so there's two kinds of mistakes. Sorry, I'm looking for something that I thought I had, but it's not in this folder. Huh. Yeah, I can't use that. You know what? Forget it. So, why is 5-ethyl octane, although it's wrong, why is it not a terrible name?
Because at least you know that if you're counting it that way, that if there's something that it's connected to the fifth carbon.
If you drew 5-ethyl octane, what would you draw? You draw that molecule,
Yeah.
right? So at least the structure is correct. So this is more like grammatically incorrect, not actually incorrect. Does that make sense? Like
Yeah.
the way Yoda talks is wrong, but you still understand what he says if you take a second to think about it, right? So if somebody wrote this, I'd be like, well, that's wrong, but it's not that big a deal. What if they had written 6-ethyl octane?
Oh.
Then it's just flat out wrong, right? That's a different molecule. So that would be a really wrong answer. So again, if we were in person and you wrote 5-ethyl octane, I don't even know if I'd take points off for it. I'd just say, hey, count from the other side. Because you still come up with the same structure. But if you wrote 6-ethyl octane, you get 0. Because that's just flat out incorrect. What else might somebody do with this molecule that would be incorrect?
Oh yeah, keep going.
Just go in a straight line. So don't get stuck in the fact that the straight line is where you're going with this, because it's not. You could call this a heptane, and you could call this a 1,2. You would call it a 3-propyl heptane, and then that's not a terrible name because I'd still get the same molecule, but it's not how you name this. You need to realize that hey, that's 8 in a row, and so I need to take my chain up here and call that the side chain. Okay, so let's talk about what we have down here. So again, what you do is you start at an end and you count till you get to an end and you ask yourself, was that the biggest number? So 1, 2, 3. Okay, so 3 carbons long. 1, 2, 3, 4, 5, 6. 6 carbons long. 1, 2, 3, 4, 5, 6, 7. Okay, so I know that that right there is the longest continuous carbon chain, the straight across. What's attached to my straight across? This and this. How many carbons is that?
1,
1. How many carbons is that?
2.
So I have a methyl side chain and I have an ethyl side chain. Where are the methyl and ethyl side chains?
On the 2 and 4.
On carbon number 2 and on carbon number 4. So the way I write this is I say heptane. And on carbon number 2, there's a methyl group. And on carbon number 4, there's an ethyl group. This is understandably dumb, but it's the way it is. This one over here is incorrect because they put the side chains in alphabetical order. So ethyl comes before methyl alphabetically, so the ethyl comes first, even though it's on position 4 and the methyl's on position 2. Sorry, but that's just the way it is. But this one over here, this is like a Yoda mistake, right? Not really a big deal. I'm going to draw the same molecule. What's wrong with this one?
6. Okay.
They just counted from the wrong side, correct?
Yeah.
Is this a big deal? No. Why? Because I'm going to draw the same one. So not a huge deal. But again, not exactly correct. Let's draw some of these things out. So let's see. Worksheets. Okay, can you name that first one for me? Actually, why don't you name 1 through 4, and then we'll come back. I'll give you a couple minutes. We good? So 1, 2, 3. So what kind of molecule is this root?
Is that 2-methylpropane?
Well, the root is prop because it's the longest carbon chain is 3. It's all single bonds, so the suffix is ane, and then the attachment to this is exactly what you said, 2-methyl. So again, dashes between numbers and letters. Okay, so what's the longest carbon chain in the next one?
Or
We okay with that? So 4 is bute. How is it just single bonds? Yes. So then it's butane. And then there's one side chain on this. It's right here. So that's another methyl group. So this is off of carbon number 2 if I start on this side. So then it's 2-methyl butane.
Can you explain that last part again? The 2-methyl.
So carbon number 1, carbon number 2, carbon number 3, carbon number 4. We okay with that?
Okay.
So that's my longest carbon chain. So what carbons are not included in these 4 carbons?
The side chain.
Okay. So what carbon is that carbon attached to?
Carbon number 2.
So that's carbon number 2. And how long is this chain? How long is this side chain thing that I have circled in red? 1 carbon. And that's what meth means, 1. And YL means side chain. So what we're saying is on carbon number 2, there's 1 carbon side chain on a 4 carbon single bonded molecule.
Okay.
How about this next one?
There's 6.
The longest continuous carbon chain is 6, correct?
Yes.
7.
1, 2, 3, 4, 5. Oh,
Did you count down?
I don't know why I started it. Yeah, I counted down.
All right, so it's 7, so that's a hept. It's all single bonds, so that's a heptane. There's a side chain on this that's 2 carbons long. So that's an F side chain. And where is it? 1, 2, 3. It doesn't matter what side I count from, I end up at carbon number 4. So 4-ethyl heptane. Okay, how about this next one?
Um, 7.
I get 7 no matter which direction. I can get 7 2 different ways, but it doesn't matter. It's still 7. So I'll make it easy on myself and just go here. So I've got another hept. And it's an ane because it's all single bonds. And I have 2 side chains here and here. What side do you want to be carbon number 1 on my main chain?
the right side.
If I do the right side, then I get a 3 and a 4. If I do the left side, then I would get a 4 and a 5. So I'll do 3 and 4. So what are my side chains? There's an F and there's a meth. Okay, so E comes before N alphabetically, so I'm going to say 3-ethyl, 4-methyl heptane.
And what's the reasoning for the YL again?
It means side chain.
Right.
So
Would
this
you use meth?
ETH means 2, but YL means side chain. So that's telling you that
Would
it's
you use them for
2 carbon
not
side chain.
Side chains?
What?
Would you use those for not side chains?
No.
The meth and the F.
No. Oh yes, absolutely. We already did.
Right.
If it's only 2 carbons long, then it's ethane.
Okay. Yes.
Leave him alone. You don't need to chase him. And put some shoes on. You're gonna get slivers on your feet out there. How many carbons do we have with this last one here? Is it 8?
Yes, it's 8. That's 7, but the side chain.
Okay, so then it's an oct. It's all single bonds, so it's an octane. There are 2 side chains. There's a 3 carbon chain, which is a prop. And there's a 1 carbon chain, which is the meth. Which side do you want to count from?
The right.
The left.
How do you know?
Which one gives you smaller numbers? If I call this one number 1 here, then it's a 3, and a 5. If I start as this is number 1, then I get a 4 and a
7 or 6.
6. So I don't count from the right side, I count from the left. So meth comes before, M comes before P. So then this is going to be a 3 methyl 5 propyl octane.
Okay.
All right.
Do you have a list of like these rules in one compact place?
Yeah, right here under
Or are we
rules.
just- Oh yeah, there it is. Amazing.
So we've got some side chain rules that we have to talk about. So if I have a 3 carbon side chain, I can connect it to the main chain in 2 different ways. I can connect it to the end, or I could connect it to the middle carbon on the side chain. Okay? So this is 8 carbons long. And if I start counting from the right-hand side, my side chain is off of carbon number 4. So this is 4, off of carbon number 4, there's 3 carbons hanging off there. So how is it connected to carbon number 4? With the end of the 3 carbon side chain. So this is 4, referring to carbon number 4 right here. It's prop because this thing is only 3 carbons long, and it's YL because this is the side chain, and then the whole molecule is 8 carbons long, so that's my oct, and it's all single bond, so there's my ane. We good with that? How is this
Yeah,
one
but
different?
Why is that one? It's connected in the middle.
Okay, so it can't have the same name because it's a different molecule. It has a different boiling point, melting point, flash point, ignition point. So it's a different substance, a different density. It's more or less chemically reactive. This one's, the one on the right's less chemically reactive. So I have to name it differently. So how do I name it differently? We use this prefix iso. And what does iso mean?
1?
No,
No.
it means different. And that's it.
Oh great.
It just means different.
Isopod.
So isopropyl alcohol is an alcohol is a name you're familiar with.
So it's just saying.
So
it's a
when I
different
say
propyl.
propyl alcohol, it would be an alcohol group on a 3 carbon chain. I'm not going to draw the H's because I'm a chemist. There's propyl alcohol written in line structure. Okay? What's isopropyl alcohol look like?
Is it connected in the middle instead?
Yep. The 2 on the right in orange are isopropyl alcohol. So what's iso mean? Different.
Different.
That's it. So you have to understand what propyl alcohol is, and the only other option is isopropyl. It's either on one of the ends or in the middle. There isn't another option. But what if I've got a 4 carbon side
So
chain?
if it starts.
Go ahead, Annika. If it starts what?
So if it's. Can a chain start on the left side and the right side and be the same or the right side and be the same molecule, like a side chain?
Is this a pen?
Yes.
Is this a pen?
Yes.
Is it the same pen?
Yes.
So it doesn't matter what end I connect it to because the molecule itself is completely symmetrical. So you couldn't tell which end it was connected to. It wouldn't chemically react any differently, so it can't have a different name. Okay, so let's talk about the next one, which is 4 carbons on a side chain. So now what I have is a base molecule that's 9 carbons in a row, so it's a non. It's all single bond, so it's a non-name. On carbon number 5, I have 4 carbons attached as a side chain. The first one is simply called 5-butyl nonane. The 5 refers to which carbon on the 9 carbons it's attached. The butyl means the thing that's attached to it is 4 carbons long. The YL means it's a 4 carbon long side chain. The non means 9 and the ane means single bonds. So this would be 5-butyl nonane. But what if it's not connected to the end? What if it's connected to the second carbon instead of the first carbon in the chain? What are we going to call it? Because it's a different molecule with different properties. So there it is right there. What do we call it?
Sec-butyl nonane.
That's telling you that on the second carbon on the butane side chain is where it's making its connection to the main chain. We good? All I did is I shifted the side chain over 1. Well, 4 carbons
So
can
it
be...
also be connected to the CH2?
What?
Could it also be connected to the CH2 and be called sec-butyl nonane?
If it was connected over here, 2 things would change. This would only be 1 carbon, or 1 hydrogen, and I'd have to put another 2 here.
Right.
But it doesn't matter which one of those I connect to, that's going to be number 2 in the chain. Just like it wouldn't have mattered if I connected it to this carbon or connected it to that carbon, it's still connected to the one on the end. Okay, but what if I connect it in a different way? I've got 3 carbons in a row, and off the second carbon, there's a side chain on my side chain. So now my side chain has a side chain. How do I deal with that? Well, it's still connected to number 5 spot on my nonane, and I'm going to call it isobutyl. Why? Because it's different. Then there's one more way to connect it up. So this way is called tert or T-butyl because it's kind of in the shape of a T. So if I've got a 4 carbon side chain connected to 9 carbons, I can connect the 4 carbons up to the 9 carbons 4 different ways. There isn't another way to do it. It's just these 4.
Oh God. This is overwhelming.
Yay, organic chemistry. Okay, next thing we're going to talk about is something we've already talked about, and it's called an isomer. So an isomer is the way I take a molecule and build it differently. So if I handed every single one of you 4 black Legos and 8 or 10 yellow Legos and said build something, you wouldn't build the same things, even if I gave you instructions as to how you were allowed to connect stuff up. And so that's why carbon is like Legos, because C4H10 applies to that and applies to that. And the rules are carbon makes 4 bonds, hydrogen makes 1 bond, start putting stuff together. So I did. And the one on the left, I just connected it up in a straight line, and the one on the right, I didn't. I made a 3 carbon chain, and then I have another 1 carbon chain hanging off of it. So these are structural isomers. They are physically connected to each other differently, which is why they're structural isomers. Here are more structural isomers. The longer the chain, the more ways I can disassemble it and put it back together. In the same way, if I gave you 50 Legos that were black and 150 Legos that were yellow, how many different molecules can you make? Many. So if I give you 6 carbons, you can make them hexane, which is a straight chain, or I can pluck one of them off the end and put it on carbon number 2 and it turns it into a pentane. Or instead of putting it on carbon number 2, I can plug it onto carbon number 3. It's still a pentane, but now its methyl group is on position number 3. I could pluck both the ends off and put one on number 2 and one on number 3, or I could put them both on number 2. Those are the only isomers for 6 carbons. Structural isomers. Are we having fun yet? Drop out of med school. That's what this does to people.
I'm not
Makes
going to med school.
Makes them drop out of med school. Okay, so next thing I want to talk about are molecules that might look the same, but are either not the same or they're actually identical to each other. So these two molecules look different when in actuality they're exactly the same molecule. Around a single bond, I have complete and free and utter rotation. They can just spin. So it doesn't matter where I draw the F on that first carbon, as long as it's attached to the first carbon. So those are not isomers, they're identical molecules. The example for that is do you know who this is?
Oh yeah,
This is Daniel. This is Daniel. We okay with that? What's this?
That's Daniel.
That's Daniel. What's this? That's Daniel.
Daniel.
It doesn't matter the orientation. So these molecules that I have on this screen over here with the fluorine and the two carbons, all I'm doing is looking at it from a different angle. It's still the same molecule. Okay, so all 6 of these structures here are the same molecule. All I'm doing is looking at it from a different perspective. Left side, right side, up, down, whatever you want to say. It's just the same thing. Because if I want to talk about the carbons and the hydrogens and the fluorine, so I'm going to describe this first fluorine right here. It's a fluorine attached to a carbon. And the carbon it's attached to is attached to 2 hydrogens and a carbon. And that carbon is attached to 3 hydrogens. If I used the same verbiage to talk about that fluorine, I would say exactly the same thing. So they're not isomers, they're actually exactly the same molecule. So how about this? Now I've added a second fluorine to it, so it's a different molecule than the first ones. And this one would be called 2,2-difluoroethane. Why? Because it's 2 carbons long with single bond, so it's an ethane. It's a fluorine, but there's 2 fluorines, so I say difluoro, and the positions of the fluorines are on carbons number 1 and 2. It could be on carbon 1,1, and then I would, on carbon number 1, both of them, so then I would say 1,1-difluoroethane. So the importance of this is to talk about chemical equivalence. Tell me about those 2 fluorines. Are they identical to each other as far as their chemical reactivity?
Yes.
No. I'm telling you right there in the chart that it's not equivalent. Tell me why it's not equivalent.
Because they're attached to different chemicals.
One of the carbons is attached to a chlorine.
So they're both attached to a carbon, but you can't just go that far. You have to keep going. So the one on the left, that fluorine's carbon is attached to a chlorine. The one on the right, that fluorine's carbon is attached to just hydrogens. So the fluorine on the left is way more chemically reactive than the fluorine on the right, which means those 2 fluorines are not identical to each other. Tell me about this hydrogen and this hydrogen. Are they chemically equivalent to each other?
No.
They are.
Yes.
Because they're attached to the same carbon. But tell me about this hydrogen over here. The one that's boxed. The answer is no, because the carbon it's attached to is also has a chlorine attached to it. So the circled hydrogen and the circled hydrogen are much, much less reactive than the boxed hydrogen because they're not connected to the same molecule. Or sorry, the things they're connected to are not connected to the same kind of substances. What about this hydrogen and this hydrogen? Well, they are equivalent to each other because this hydrogen is connected to a carbon and that carbon is connected to 2 carbons and a hydrogen. And the carbon on the right is connected to 2 hydrogens and a fluorine. And the carbon on the left is connected to 2 hydrogens and a carbon with a carbon, 2 hydrogens and a fluorine. And I would say the same thing if I talked about this hydrogen. In actuality, all 4 of these hydrogens are chemically equivalent to each other. And all these hydrogens that I have circled, all these hydrogens that I have circled in green, they are all chemically equivalent to each other. but they're not chemically equivalent to the ones that I have circled in red. Um, sorry. Okay, so cyclic alkanes. Sometimes the molecules come back on themselves and make rings. So we saw that with benzene, or in this case, we have a cyclic alkane, which is cyclohexane. So the formula changes because now I don't have the ends empty. So the ends come back around and all the carbons are attached to 2 carbons. So the formula changes from C6H14 to C6H12. So I literally just double the number of hydrogens to get my formula. And then I just call it cyclohexane. And that's it. That's the extent of its nomenclature. So let's name these 2 molecules, number 1A and B.
Okay.
What? It's close. What? Password? Keys in the Tupperware container to the right of the gun. What's the longest continuous carbon chain? We okay with it being a deck? Okay, so I'm gonna say deck. It's all single bond, so it's a decane. The side chains are this bromine, this propane, and this methyl group. So this is, I'm going to start from this side. 1, 2, 3, 4, 5, 6. So alphabetically, bromine comes first. So this is 5 bromo, 6 methyl, 5 propyl decane. Are we okay with that? The next one, if it's a cyclic structure, that'll be your base structure. So this is 6 carbons in a ring structure. So I'm going to call that cyclohexane. What's attached to it? Well, there's a methyl group here and a methyl group here and a bromine group here. Since it's a circle, I can pick any one of those I want to be number 1. So I'm going to pick the one with the bromine on it because that's algebraically superior. So 1 bromo, 2, 3 dimethyl cyclohexane would be the name of this molecule. We good with that? Okay. I'm going to go ahead and call it a day. And you guys will have homework problems dealing with this kind of stuff, and then we'll finish up the notes on Tuesday. Have a good day.
Thank you.